Hello, hello! Here is the video going over our pre-calculus functions quiz review. This video will talk about finding the domain of functions algebraically, function operations including adding, subtracting, multiplying, and dividing, as well as the composition of functions, and finding the inverse of functions. So here we go. The first thing we're going to do is find the domain of different functions and to write the domain in interval notation. So if I look at number one is a square root function. One key thing that we always have to remember about square roots is that we cannot take the square roots of negative numbers because they do not result in real numbers. They are imaginary numbers. So what that means is that everything underneath that radical has to be positive or equal to 0 because you can actually take the square root of 0. Positive numbers are greater than 0. So this actually results in an inequality. I have 9 minus 3t, and that has to be greater than or equal to 0 because that will give me positive numbers or a 0, which I can take the square root of. So now from here, I just need to solve this inequality. So I'm going to subtract 9 from both sides. That gives me negative 3t is greater than or equal to negative 9. Divide both sides by negative 3. One thing that you do have to remember with inequalities is anytime you are dividing by a negative, we do need to flip the sign. So instead of this being a greater than or equal to, it now flips to a less than or equal to, and negative 9 divided by negative 3 is a positive 3. So there is our domain as an inequality, but we do want it in interval notation. Sometimes the easiest way to figure out our interval notation is to actually graph it. So t is less than or equal to 3. That means at 3, I can include that value. So that is a closed circle for my inequality. And that is going to be everything to the left, since I want it to be less than or equal to 3. So that is from negative infinity up to 3. And so to write that in interval notation, my domain is going to be negative infinity with a parenthesis to 3. With a bracket. And we use the bracket in this case because that 3 is a value that works for the domain. So essentially anytime you have a number line and you're graphing an inequality, if you have a closed circle, that is going to be a bracket. Open circle will be a parenthesis. All right, number 2. Number 2 is just a regular polynomial. It is a quadratic function. Your domain for quadratic functions are always all real numbers. There aren't any issues with domain when it comes to polynomials or quadratics, just because you can plug in anything for your x, or in this case k, and it would actually result in a real number. So number 2 is negative infinity to infinity in interval notation. Number 3, I have a rational function. Rational functions give us issues with domain because we cannot divide by 0. So essentially, this denominator cannot be 0. My numerator, on the other hand, can really be anything. That's not going to give us any sort of issues. It's just the denominator that we are going to focus on since we can't divide by 0. So 2x plus 4 cannot be 0. I'm going to go ahead and solve this to find exactly which value of x we cannot have. So I'm going to subtract 4 from both sides. That gives me 2x cannot be 4. Divide by 2. So, negative 4. Lost my negative. So that means x cannot be negative 2. And once again, sometimes to figure out our intervals, it's helpful if you actually graph it on a number line. So since x cannot be negative 2, I'm going to go ahead and put an open circle there. And essentially, I can have any value for x except negative 2, because negative 2 is going to give me that 0 in the denominator that we cannot have. So this in interval notation would give me the domain of negative infinity up to negative 2 and negative 2 to infinity. So essentially, it is that domain of all real numbers without the negative 2. So that's why you have that break in the domain. Number 4 is very similar to number 1. We have that square root. So 2n minus 8 has to be positive or equal to 0. I'm going to add 8 to both sides. So 2n is greater than or equal to 8. So n is greater than or equal to 4. Again, just to make things easier, I'm going to graph this on a number line so I can figure out what my interval is. Everything that's greater than 4 is everything to the right of 4. So that domain in interval notation goes from 4 with a bracket, since 4 is included, to infinity. All right, let's keep going. Number 5, I do have a square root in a rational function. So my denominator cannot be 0. I'm going to go ahead and make a little note. This cannot be 0. And also because it is a square root, it also has to be positive. So everything underneath my radical has to be positive. So negative 2x plus 9 has to be greater than 0. If you'll notice for this particular inequality with the radical, I didn't use the or equal to because this radical is in the denominator. And again, if I look at my numerator is just a linear function. Linear functions are not really going to give me issues with domain. So I'm going to go ahead and ignore my numerator. Once we get to number 6, I will not be ignoring the numerator anymore, just because my numerator is now a square root. And square roots and rational functions are the ones that are going to give us more complex domains. Continuing with number 5, I'm going to subtract 9 from both sides. That gives me negative 2x is greater than negative 9. Divide by 2. Again, I am going to flip my inequality since I am dividing by a negative. So this becomes x is less than positive 9/2, also known as 4.5. I'm going to go ahead and graph that on a number line just so I can figure out where my interval is. So 9/2 is 4.5. And x has to be less than 9/2, so that's everything to the left. So my domain goes from negative infinity to 9/2. Both of those have parentheses. Infinities will always have parentheses. But for this one, since it cannot equal 0, your 9/2 is an open circle, so the interval is going to have a parenthesis instead of a bracket. All right. Number 6. So number 6 has several things going on. So we have this radical on the top. So again, with radicals, we cannot take the square roots of negatives. So x plus 2 has to be positive. So I'm going to make that greater than 0. Since this is in the numerator, it is perfectly fine for the numerator to be 0. So I'm going to go ahead and make that a greater than or equal to 0. So solving this inequality, this tells me that x has to be greater than or equal to negative 2. So I have that piece of information for my domain. Now let's deal with this denominator. So this denominator cannot equal 0. We have this quadratic this time around. So anytime we do see quadratics, chances are we're going to have to factor it. So in order to factor this, I am trying to find two numbers that multiply to negative 24 and add to 5. Make these little notes here. So I want to find two numbers that multiply to negative 24 and add to 5. That is going to be a positive 8 and a negative 3, and that product cannot equal 0. So essentially, x plus 8 cannot be 0, and x minus 3 cannot be 0. So for my first one, x cannot be negative 8. For my second one, x cannot be 3. So now I'm going to take all three of these pieces, and I'm going to put them on a number line to see what it is that we're working with. So let's see. I have negative 8 over here. X cannot be negative 8, so I'm going to make that an open circle. I'm going to go ahead and put negative 2 over here. Obviously, my number line is not drawn to scale because I'm not putting all the numbers in between. So ignore the spacing in between. It is not accurate. X also cannot be 3, so I'm going to put an open circle at 3. Close my circle at negative 2 since negative 2 does work, and I want everything that is greater than negative 2. So greater than negative 2 would be everything to the right except that negative 3, except that positive 3, since x cannot be positive 3. So when I write this as my domain, I have the interval from negative 2 to 3, and then everything past 3, so 3 to infinity. That negative 8 didn't even matter just because it was not part of our shaded region once we actually graphed the inequality. All right, so those are all of our problems dealing with finding domain algebraically. Next thing we are going to look at are function operations. So I have three functions over here. I have f of x is x squared minus 4x, g of x is x minus 1, and h of x is 1 over x. So the first question says to find g minus f of x. So I'm going to take my g function. Another way to write this is just g of x minus f of x. I'm going to color coordinate a lot for this since we're looking at several functions. So essentially I want to take my purple function minus my pink function. So my purple function is x minus 1 minus my pink function, which is x squared minus 4x. If you'll notice, I did put that x squared minus 4x in parentheses since I am subtracting both of those terms. I'm going to go ahead and distribute that minus into my second function, so that gives me x minus 1 minus x squared plus 4x, because I distributed that minus. I'm going to go ahead and rearrange this and write this in standard form. That gives me negative x squared. I have these two like terms, x plus 4x is 5x, and minus 1. So there is my resulting function of subtraction. And for this one, I do just have a quadratic function, which doesn't really give us anything too special with domain. So that domain is going to be all real numbers, negative infinity to infinity. All right, number 8. So number 8, I am taking the composition. So I am taking f of g of x. So what that means is I am going to take f of g of x, which is x minus 1. So essentially what I'm doing is wherever I see an x in my f function, I'm going to replace it with x minus 1. So the first part of my f function is x squared. So instead of x, I'm going to put in an x minus 1 minus 4 times x. But again, instead of my x, I'm going to put in this x minus 1. So the composition of a function is taking one function and literally putting it into the other function. And then from here, our job is just to simplify. So just be careful as you're simplifying this. X minus 1 squared is the same thing as x minus 1 times another x minus 1. This negative 4 I can go ahead and distribute, so negative 4 times x is negative 4x. Negative 4 times negative 1 is positive 4. And then I'm going to multiply these two binomials. So x times x is x squared. X times negative 1 is negative 1x. Negative 1 times x is negative 1x. Negative 1 times 1 is a positive 1. Bring down the minus 4x plus 4. And then we just combine all of our like terms. So we have x squared, let's see, negative 1x minus 1x is negative 2x, minus another 4x is negative 6x, and then plus 1 plus 4 gives us plus 5. Another quadratic again, which means our domain is all real numbers, negative infinity to infinity. All right, let's see what number 9 is. Number 9 is another composition. I am taking h of g of x. So what that means is I am taking h of g of x, which is x minus 1. So wherever I see an x in my h function, which is just on the bottom of that fraction, I'm going to replace it with x minus 1. And this cannot be simplified any further. So our composition for this one is just 1 over x minus 1. Now this does have issues with domain because it is a rational function. So down here, x minus 1 cannot be 0. So that means x cannot be positive 1. So my domain for this will be all real numbers except 1. So I'm going to go ahead and take out 1 from my interval of all real numbers. Whoops. So I have negative infinity to 1 and then 1 to infinity. And number 10, I am taking h of x, which is 1 over x times g of x, which is x minus 1. I can go ahead and multiply straight across to simplify this, and that gives me x minus 1 over x. Whoops. Yeah, over 1. Multiply straight across, and that gives you x minus 1 over x. So for this particular function, after we multiplied them, our denominator cannot be 0, so x cannot be 0. So my domain for this one is going to be negative infinity to 0, and then 0 to infinity. All right, let's see what number 11 is. So 11 and 12 are both going to be using these graphs. So it says use the graphs of f of x and g of x to calculate f of g of 1, g of negative 2, and then g of f of 0. Okay, that one's a mouthful. Okay, so let's start with f of g of 1. So anytime you're working with the composition, you always want to work from your inside out. So I'm going to start by finding g of 1 first. So I'm going to look at my g graph. G of 1 is right here. So the y value, my x value is 1, is 0. So now I'm going to find f of 0. So with the composition, when you're working with actual numerical values, the input results in an output for the first function, and then that output becomes the input for the outside function. So now I'm going to go to my f graph and find my x of 0, find that corresponding y value, and that is 2. So that means f of g of 1 is 2. All right. G of negative 2. So I'm going to go ahead and start by finding g of negative 2 first. So looking at my g function, I'm going to go to an x of negative 2, find that y value, which is 3, and now I'm going to find g of 3. So I'm going to go to my x value of 3, find that y value, which is negative 1. All right, let me clear off my graphs so I can use them later. F of 0. So I'm going to start by finding f of 0 first. So always working with my inner function first. So f of 0 is 2. So now I'm going to find f of 2. F of 2, ooh, we got something funky going on at 2. 2, we have this break in the graph. So right here, anytime you have a break in the graph, you're always looking for the one that has the closed circle. So that value with the closed circle is 3. So be careful with that. Do not pick 0, because 0 has the open circle. Okay, so now I want to find g of 3. G of 3 is negative 1. So there you go. So just be careful for this one since you are picking a portion that has a break in the graph. Number 12, using the same graphs from 11, what value of x would make this statement true? So essentially you're going backwards. So what I want to do is the resulting output is going to give us negative 3. So I want to find f of x equals negative 3. So I want to find which x value gives us a y value of negative 3 on my f graph. So my y value of negative 3 is over here. There it is on the graph. That corresponding x value is 3. So now that means g of x is going to equal 3. So instead of your input becoming the output for your next function, you're now working your way from the outside in. So negative 3 was the output of the f function, so we wanted to find the corresponding input. That's where this 3 came from. And now that 3 becomes the output for the g function, so I want to find what was that corresponding input. So I'm going to go to my g graph. I want to find the x value when my y value is a positive 3. So y value is a positive 3, hits the graph right there. That corresponding x value is negative 2. So that right there is actually your final answer. x is negative 2. And what you can do to check it is you can actually do f of g of negative 2 to make sure that the result is actually negative 3. So let's test that out. So g of negative 2, so now going in the opposite direction, like you would normally do. Normal direction, I should say. So g of negative 2 gives me 3. And then when I find f of 3, that gives me negative 3. So that statement ends up being true. All right, next up, inverses. So find the inverse and its domain, show all work. So one thing that you have to remember about inverses and their domain is the inverse's domain is actually going to be the range of the original function. So I'm going to go ahead and write this as g of x. So for g of x, the domain, since this is a linear function, your domain is all real numbers. And the resulting range of a linear function is also all real numbers. So that means when I'm finding the inverse, so the inverse we denote with the negative 1, that means these two essentially switch. So my range becomes my domain of the inverse, which for this one is not really anything special since they're both exactly the same, but you'll see it a little differently with the next example. Okay, so now I'm actually going to find the inverse. So in order to find the inverse, I'm going to go ahead and change my function notation into just regular y equals. So I have y equals 2x minus 3. To find the inverse, you're literally going to switch your x's and y's, which is why your domain and ranges end up switching, because your domain are your x values, your range are your y values, and you're literally switching them when we're talking about inverses. So the next step is to solve for y. So I'm going to add 3 to both sides. That gives me x plus 3 equals 2y. Divide by 2. And I get y equals x plus 3 over 2. And we can write that in function notation. Oh, this is a g function. So I'm going to write g inverse of x equals x plus 3 over 2. Or if you want to get fancy, you can separate that fraction and write it as x over 2 plus 3 over 2. Either of those should work for your inverse. And once again, the domain of your inverse comes from the range of your original function. And the range of my original function was all real numbers. So my domain is all real numbers. All right, let's do another one. For this one, I have my square root function. So your square root function, you gotta kind of have to be careful because of your domain and ranges for this. So since we really just want to find the domain of the inverse function, I'm gonna focus on the range of my original function. Now with square roots, it might be easier to explain if I actually graph it. So if we think about our transformations unit, plus 2 on the inside means my square root function is moving 2 units to the left, and plus 1 on the outside means my square root function is moving up 1. So normally our square root function looks like this. But because of my shift, I am moving 2 units to the right, and then, or 2 units to the left, and then 1 unit up. So now my square root function is doing something like this. Okay, so if we look at the range of what I have in pink, my range are what my possible y values are. And it starts at positive 1 and is everything above that. So my range for my original function is going from 1 to infinity. And that is actually going to become our domain for the inverse function. So I do already have my answer for my domain. It's 1 to infinity. But let's go ahead and find the inverse. So my inverse, I'm going to go ahead and switch my x and y's. I'm going to go ahead and write it as y equals first. And I'm going to switch my x and y. So I have x equals square root of y plus 2 plus 1. I'm going to add 1 or subtract 1 from both sides. So x minus 1 equals the square root of y plus 2. To undo a square root, I'm going to go ahead and square both sides. So then that leaves me with x minus 1 squared equals y plus 2, because your square and your square root are going to cancel on the right-hand side. And then last step is to subtract 2 from both sides. So I get y equals x minus 1 squared minus 2. We can go ahead and write that in function notation. F inverse of x equals x minus 1 squared minus 2. Now, if we look at what we had in the end for our inverse was a quadratic. And normally with quadratic functions, its domain are all real numbers. But because we did take the inverse of a square root, we do have these limitations for square roots, which is going to result in a limitation for the domain of the inverse. So once again, your domain of the inverse is the range of the original. So let me make a note. Domain of the inverse is the range of the original function. So be careful with that. All right, last couple of questions. We are finding inverses of graphs. Oh no, there's still more. Are the following, I haven't gotten to the graphs yet. Are the following functions inverses? So to determine if two functions are inverses of each other, I need to take the composition. So you can take the composition in one of two ways. You can do f of g of x, or you can do g of f of x. And what you're looking for is you want both of these to equal the function x. So I'm going to go ahead and take the composition. I'm going to do g of f of x, because that's just what I feel like doing. So I'm going to take my f of x and put it into my g of x. And let's see what happens. So instead of x, I'm going to put negative 5x minus 7 plus 7 all over 5. And let's simplify this and see what it gives us. So negative 5x minus 7 plus 7, that's going to give me negative 5x over 5, which reduces to negative x. Our goal is to just get x, but we got a negative x. So what that means is that they are not inverses. So your goal is to just get x. Not negative x, not x plus 1, but just x. And since they are not inverses, we don't really need to check that f of g of x is going to equal x either, because if it doesn't equal for one of them, it's not going to equal for the other one. All right, here we go, another one. So again, we can do f of g of x or g of f of x, and we want to see if it equals x when we're trying to verify. So I'm going to go ahead and do f of g of x. So I'm going to take this and put it in for x into my f function. So that gives me 2 times, instead of x, I'm going to put the cube root of x minus 5 over 2 cubed plus 5. The cube and the cube root are going to cancel itself out. That's nice. So that gives me x minus 5 over 2 plus 5. And then these two, since I'm multiplying by 2 and dividing by 2 at the same time, they are also going to cancel. So that leaves me with x minus 5 plus 5, which equals x. Now I'm going to try it the other way. So now I am going to take, I'm going to go ahead and erase this up here. Now I am going to take my f of x and put it into my g of x and see what happens. So I have my cube root, but instead of x, I'm putting 2x cubed plus 5 minus 5 over 2. Okay, my 5's are going to cancel out because 5 minus 5 is 0. That leaves me with 2x cubed over 2. Ooh, my 2's are going to cancel out. This is working out real nice. So my 2's are going to cancel out. That leaves me with the cube root of x cubed, which is x. So we verified that both of them ended up being x, so that means yes, they are inverses of each other. Yay. All right. Last question is when you are finding the inverses of graphs. Okay, so when you're trying to find the inverse, you're always switching your x's and y's, right? That's what we did when we were actually finding the inverse. When we were talking about domain and range, we were switching the x's and y's. So that's exactly what I'm going to do for this. So I'm going to go ahead and make a table of my original point values. So this point right here is -3, -2. This point is 0, 4, and this point is 4, 2. And for my inverse, I'm literally going to switch my x's and y's. So this becomes -2, -3, 4 and 0, and 2 and 4. And I'm going to plot those points. So -2, -3 is right here. 4, 0 is right here. And 2, 4 is right here. And I'm going to connect these points. And voila, there's our inverse. One thing about inverse functions is that they are reflections over the line y equals x. So if I draw the line y equals x, I should be able to see that they mirror each other. Yep, that one worked out nicely. All right, let's do the next one. The next one, I have lots of points this time. So this point is -5, 2. This point is -3, 0. This one is 0, 3. 3, -3. And 5, -2. Gonna go ahead and flip those around for the inverse. So this becomes 2, -5. I'm going to go ahead and graph as I flip. So 2, -5 is right here. 0, -3. I'm actually going to connect as I go because I do have a lot of points that I'm connecting. And when I see a bunch of points together, my brain's going to get confused on how to connect them. Next up is the inverse of 0, 3, which is 3, 0. 3, 0 is right here. Okay, and then 3, -3 becomes -3, 3. -3, 3. Go ahead and connect those. And 5, -2 becomes -2, 5. -2, 5. And voila! And once again, you can see that my purple and my pink functions are mirrors of each other over the line y equals x. All right, so that covers all of the questions in our functions quiz review. Good luck on your quiz.